Okay, we are coming to the more sort of juicy parts of the pipeline, if you can call it that at all. Let's see now. Shaders. Vertex shaders. As I said, what you need to remember first and foremost about a shader is that it's really a little program. It's a bit strange, this term, where it comes from, but it's a small program that runs on a GPU. And a vertex shader is a small shader program that transforms vertices. For instance, when you see a scene, if you have a game that's made in Unity or something like that, and you see a scene with a lot of objects in it, these objects are placed in the world space in different positions, and they move in relation to each other, and that's what the game is, maybe. This position in the world and their orientation and rendering all those in the right places, that is the vertex shader that takes care of that actually places them in the right positions. Now, the main topic of the next time is these what is called affine transforms, which is how we transform objects and rotate them in 3D space. And all of that stuff is done by the vertex shader. So really what that whole course is about, topic is about, is how to write vertex shaders. But here we're going to look at it more in a general way. What is a vertex shader generally? So I will put a vertex shader in the middle. This and a classical black box. This. What is this? As I said, maybe a little bit before also about the inputs. There are a bit more inputs to it than just vertices. But we'll call these vertex attributes. So that is the positions, the normal vectors, the texture coordinates, colors, and so on associated with each of the vertices. The other input is something called uniforms. And a uniform is just, uniforms are parameters that don't change per vertex. So usually geometry is rendered as big chunks of vertices, like the dolphin we saw before was maybe a couple of hundred vertices. And you have like modern games on the new consoles with very high detailed graphics. Each graphical object there has a lot of vertices, like thousands or tens or hundreds of thousands of vertices. So that's one object with like 100,000 vertices, maybe a very detailed character model or something like that. And the uniforms is a value that don't change, that is the same for all these vertices. So it could be something like the general color of the object or its general position. And we call that a uniform. This is a term we use also in the programming language that we will use. Oh yeah, I just put this. What it is, a small GPU program run once per vertex. This little parenthesis. Yeah. A bit of color. So that goes into the vertex shader. I mean, the vertex shader is a program, so it's some code that you write. That's inside the box. And what comes out, we call that vertex position, that's the most important, and that is in screen coordinates. So the object is defined as object coordinates, we call it. We want like local coordinates to the object, so we can draw an object anywhere in the world and orient it in a certain way. That transformation is done by the vertex shader, and the rest of the graphic rendering hardware doesn't really know about anything else than screen space. So it knows where stuff is on the screen. It doesn't know anything about the 3D world that we have, or even where the objects are placed. It just knows the coordinates of each pixel on the screen. And because we use some generalized version of linear algebra to do this transformation, it can all be done with a single matrix multiplication, and we can see that later. And then another thing we get out is something called varying variables. I know that sounds a bit strange, but again, this term varying is actually from GLSL. I think it's from this programming language. It outputs the positions of each vertex in the scene, but also output these varying variables, which is something that is interpolated across the surfaces that we later draw. So that could be a color, a light value, texture coordinates. And clarification outputs. Isn't it? And in the same way about fragment shaders, the first input is interpolated values, or these varying. Just this size bar. Okay. Varying interpolated values. These don't come. It's important to understand that they don't come directly from executing a fragment shader. I mean, they are. It's like the fragment shader is first, the vertex shader is first in the pipeline, and then the fragment shader is later. So data flows through the vertex shaders and to the fragment shaders, but it's not a one-to-one connection. So it's not like the output of one vertex shader program goes into one fragment shader. It's a little more involved than that. And there's also a step between, which is primitive assembly. So from that comes these varying interpolated values that the fragment shader can work on. That's input. I'll put this. And there are some positions also. The fragment shaders also get told every fragment that gets rendered, which becomes like a pixel on the screen, knows about exactly where it is on the screen. So it's possible to do some effects based on that, based on the screen position. A normal fragment shader for lighting and stuff like that doesn't actually use the position on the screen for anything, but it's more something that is possible to use. It's available to the fragment shader, and sometimes it uses this for various special effects. For instance, if you want to do post-processing effects, like light bloom or blur, depth of field, stuff like that, then you would normally have a fragment shader that actually relies on this position on the screen. And finally, the uniforms as well. General parameters that are used to control what is happening on a constant value basis. Same value for all fragments that are rendered to render a single object. And the outputs, well, in general it's like this. There are a few exceptions, but we don't care about those for now, because the important thing is that this single important output of a fragment shader is just a color. The fragment shader is just a little program that takes all these values and makes some calculations, and then output this pixel should be this color. That's all it does. And here, a small GPU program run once per fragment pixel. And maybe some little arrows. Yes. I'm just going to open this, where was that? This pipeline version that I have drew earlier. It's in here. This one. So we can see where we are. I mean, what we talked about right now was vertex shading and fragment shading. These two steps in the pipeline. And now we're going to talk about the rest, what that is. I'm going to explain a bit about that. So if we look at it from this end, vertex data comes in from the CPU, and the vertex shader takes care of transforming it and putting it in the right place on the screen, and maybe calculating some other data for the fragment shader to use, other graphical effects, stuff like that. Outputs transformed vertices. The stage that receives these transformed vertices is called primitive assembly. And this is where vertices are turned into primarily triangles. And we call them primitives because we can also draw other stuff than triangles. But triangles is the predominant primitive that is used in this kind of application. Primitive assembly. I'm going to draw just examples of what we mean by the word primitives. So the first kind is points. A point is actually a primitive. It is used sometimes. We sometimes draw points. I mean, it doesn't really make sense to draw a point because you can't see a point. It has zero extent. But you can draw something that's similar to a point, which is defined only by being in one place in space. We sometimes have in graphics applications something called point sprites. If you think of particle systems, like graphical effects with smoke, fire, stuff like that, then each the little, like it's some smoke that's evolving on the screen or some fire or something, it's actually drawn by using a lot of little quads, or little squares of texture. But the point is that they are actually defined by being somewhere in space. and then they're oriented so they face the screen, but they don't really, well, they get bigger and smaller, but they're not oriented in any way, so they are just defined by where they're in space. So this is an example of points, but it's not used that much. And then of course a line. A line is also a primitive. If you see wireframe graphics, stuff like that, or some meshes that have the edges highlighted, then it's done with line rendering. And the primitive assembly stage is configured by the CPU to issue lines to the rasterizer. So not triangles, but lines. And then of course triangles. A little triangle. Primitives consisting of 3 vertices. And we also often work with something we'll call quads. I think the proper term for that is like quadrilateral. So we shorten that to quad. It's a vierkant in Danish. It's just a polygon with 4 sides. Most graphics APIs have, you can tell it to draw a quad because it's convenient when you are sometimes to draw quads, especially if we draw 2D stuff, we almost always draw quads, but it's usually implemented by drawing 2 triangles because the graphics hardware is simpler that way, so it only draws triangles. But the quad is also a primitive. Oops. Then there are 2 more kinds of primitives that I will show you, or techniques for rendering primitives that are quite commonly used to optimize drawing. That is triangle strips and triangle fans. So a triangle strip is a connected set of triangles. So you could maybe have something like this. That is a triangle strip. It has 3 triangles in it. The point is that it's really no different from rendering 3 separate triangles, but we can do it using less vertices because the vertices overlap. So the GPU has a processing pipeline for vertices, and if we organize everything into triangle strips instead of separate triangles, we can actually draw one triangle by using just 1 vertex, because each triangle actually reuses 2 vertices from the previous triangle, so it saves on processing power. In practice, most graphics applications that draw any kind of geometry, any kind of mesh data that is imported from a 3D package or something like that, almost always uses triangle strips to draw it because it's faster. I'll just annotate. So of course, we start the strip, we need actually 3 vertices before we can draw just 1 triangle, because that's obvious. But then we can just give like 1 more, and then the hardware knows, the primitive assembly unit in this case, knows that it should take the 2 previous vertices and add the other one and make a new triangle like this. So here we have 3 triangles with 5 vertices. And that is called a strip. Triangle fans. It's just a different way of ordering the vertices. It's mostly interesting to sort of understand the concept of these strips and fans. It's rarely used. The point is that you could do this another way, where you actually, the first vertex you give, you just keep that for all the primitives. So here we have like 5 triangles, and they all share the same vertex here. So that's why it's called a fan. It's like a Chinese fan or something. 0. Let's draw it from this side. There is something about winding order. I will get into that later. But just to quickly mention that it's not a coincidence that I put them in this way. So if you it's like, this is like, if you go around the triangle 0, 1, 2, then you're going around sort of against the clock in that winding order. And that is actually important, because normally when we draw geometry, we only draw them on one side, so if they are back facing, Like if the winding order was always looking at it from the other side, then the graphics hardware would color it away and not draw it. And for this reason, it's important to be aware which is the winding order. If you construct geometry yourself, like in a class like this, where you write a little program and put in some coordinates, then you have to be aware of this winding order, because you might get nothing on the screen if you have backface culling enabled. So that's an optimization that the GPU does. Yeah, so this is a fan, triangle fan. I'm going to do one more, because that's the last one. Coming back to this. This is rasterization I'm going to talk about. So the primitive assembly stage takes a bunch of vertices according to how it's set, like it's set which primitive it's set to render, like lines or triangles or triangle strips. And then what it does, it actually outputs triangles to the rasterizer. Say, now I want to, the rasterizer only renders triangles. So it's given like 3 screen vertices, and the rasterizer does it convert that to pixels. So figure out, given these 3 points, which pixels on the screen need to be colored. Yes, rasterization. I think I did. Let's see, actually switch this on to draw some parallel lines. Gray. Yes. I'm just going to quickly draw a little grid. Yeah. The rasterizer always gets a screen space triangle as input. So we will have a grayish color, draw a little triangle here. And what it really gets as input is the vertices, the rest is just implied. So vertex, vertex, vertex. Another term for this is projected triangle. Projected just is another way of saying that it's turned into screen space. The triangle is defined in screen space. So there is a transform which is called a projection transform, which gives the perspective of a 3D application, if it's a 3D application. Oops. So I'm going to copy this on the other one, and that. So the rasterizer just figures out where is this in terms of pixels, and then it just very simply colors all those pixels. So I'm gonna hand rasterize this triangle. Turn on this. Glad we don't do this ever. It's very boring. Must be for you as well. As you can see, I'm just basically coloring all the squares, all the pixels that the triangle supposedly intersects. I should probably take this pixel with me. Why did I do that? Should be more, right? This. I'm gonna move the triangle in front so you can see it. There. Go away and... Oh, did I put that on the background? That was not very clever. Put another one so we can see it. Something like that. That's what the rasterization hardware does. Now, as you see, what I did was I simply picked all the pixels that were in any way touched by this triangle. Some of them are... let me just swap this. This will not yield a very good result. If we combine it with other stuff, it will look a bit strange. So you can also view the rasterizer as a sampler that samples the geometry. So let's imagine that we have like two adjacent triangles that we want to render, like this. So we're just gonna focus on this edge between the triangles here. So I'm just gonna put something here that says there's more stuff here, and we make one triangle red, like this, and the other one we will make blue, like that. So let's have a look at that. This, I'm going to project this as well. So, what happened? Where did that go? Just a minute. Oh, it's this one. Okay. So maybe we want to draw it here. So the simplest way to sample this geometry is to midpoint sample it. So we sample the midpoint. We simply say the middle of each pixel, which triangles does that hit? So it's colored that way. So this pixel here is actually no color at all because they are not overlapping enough. This pixel here gets red, and the next one gets red, and this one probably red also. So fill this with some red color. Oh, I should turn on this. And here is the midpoint is not covered by the triangle. Here it probably is. So it also becomes red. And this one, midpoint is not covered by the blue triangle, but these three are. So we color those blue. And again,
like one blue and two red.
So did I do it wrong?
I mean,
Yes.
the two on the bottom are red and the top one is blue.
Thanks. I'm not thinking. You're right, because in this pixel here, the midpoint is actually in the red triangle. Great. Glad you're still awake. And this one is actually blue as well. And here we probably get this one blue. And then the other one should be red. There. Hold on, I just have to find this. Ah, okay, it's drawing the same. Never mind. Yeah. So this is how the rasterizing hardware works. There are more elaborate ways of doing this. For instance, it might be nice to have some color in between here, so maybe an anti-aliased kind of rendering where the edge isn't hard like this, but it becomes anti-aliased. So we would see that maybe 75% of this pixel is covered by the red triangle and 25% is blue. Then it should be 75% red and 25% blue. And that's what that anti-aliasing hardware could do that. But in this example here is not anti-aliasing, so we get these jaggies that we call them. We get these pixels. And you actually often see those still in applications today because it's faster. Anti-aliasing is quite slow. Yeah. Let's save this. On this stage, then it's really about just figuring out what pixels, what fragments are covered by each triangle, and then that data is output to the fragment shading unit, which then executes a fragment shader once for each of these pixels. So in this case here, there would be like 6 executions of a fragment shader for the red third triangle and like 5 for the blue one. Okay, that's about it for the pipeline. I'm not going to go so much into detail about the last part. It's just some minor operations that happen on fragments, namely depth buffering and blending, but they are also for a later lecture. The next step is to do some more practical stuff with Unity, but maybe another break. 10 minutes.